Today I want to discuss a metric space. This sounds a bit out of scope because we're currently in linear algebra, but eventually we want to introduce what is a norm and also what is a scalar product, and very eventually what is a Hilbert space. And for this we first of all need a couple of notions, like a metric. We need to know what does it mean if a metric space is complete and so on. Also in machine learning there are various applications. Nearly every machine learning algorithm in the background somewhere uses a metric, the simplest being the k-nearest neighbor algorithm, or the class of k-nearest neighbor algorithms, which we can use for all different kinds of purposes. So let's get us started with metric spaces. Let's write down the definition. First of all, we start with a set of objects. So let X be any set. It can be anything. Think about molecules, texts, images, whatever you might think about. And now I want to say how does a function look like that lives on that space and is called a metric. So a function d that lives on x times x, so it takes pairs of inputs of data points and maps them to a real number. Such a function is called a metric if the following conditions hold. We have for all u, v, and w which are in our space, we have a couple of properties. The first one is a metric is always a non-negative number. We don't want to say a distance between two objects is -5. This somehow doesn't really make sense, at least it doesn't fit to our intuition. So this is something we do not want to have. So we say the distance of xy is always larger than 0, at least if x and y are not the same. So if we have 2 points which are distinct, then their distance should be something that is actually positive. And the next thing we want to have is that the distance of an object to itself is supposed to be 0. And the distance of an object to itself is supposed to be 0. There are various ways in which this axiom can be formulated, but this is the way I've now picked. The second one is symmetry. We want that this distance from x to y is the same as the distance of y to x. So we want to have d of xy is the same as d of yx. Note that while this is natural in some applications of machine learning, so for example, if you look at distances between molecules, for example, there's no reason to think that this distance is not symmetric. But there are many other applications where it's not a natural axiom. For example, if you ask people to judge, I don't know, who are your friends? Maybe I say that Tina is my friend, but maybe Tina doesn't say that I'm her friend. So this might be a non-symmetric relation. That happens quite often, and then in machine learning we have to think what to do about it, because then the function is merely a dissimilarity function but not a metric. But for being a metric, this is what we require. So this is symmetry. And then we have the triangle inequality, which goes as follows. The distance between, if I look at 3 points, maybe I write it down first. The distance of uv plus the distance of vw is always larger or equal than the distance of u to w. Let's maybe make a little figure for illustration. If we have u, v, and w as points in our space, then the thing says, if I look at the distance sorry, this is a bit shaky. It's hard to draw it on the table if the hand doesn't rest. So if you look at the distance between u and v, and you look at the direct distance, this is supposed to be shorter than if you take a detour. So if you take a detour and you first go from u to some other point v, and then you go from v to w, this detour should be longer, or at most it should, at least it mustn't be shorter than the direct way. This is what the triangle inequality says. Okay, and taken together, whenever we have all these axioms, the function d is called a metric. Now we want to talk about what does it mean for sequences to converge to be Cauchy sequences. We have a couple of concepts that originate from topology. We look at the simplified concepts as we need them just in a metric space. You can also define all these concepts much more general, but this is not the purpose of our lecture here. We assume that we're in a metric space setting, and there many of the concepts in topology are a bit simpler than in general topological spaces. So here are a couple of further definitions. First of all, what is a Cauchy sequence? A sequence xn in a space, in a metric space X, or maybe sometimes I also, the way we are often going to write this is x comma d, so we write the space and we specify what is the distance function we are currently using, the metric. So a sequence in a metric space xd is called a Cauchy sequence if the following conditions holds. I first write it down. For all epsilon larger than 0, there exists a capital N, a natural number, such that whenever you look at indices in your sequence that are larger than n, then the distance between point xn and xm is smaller than epsilon. I hope that many of you have seen this definition before, but for those who have not, maybe I give the 5-minute or the 2-minute introduction to a Cauchy sequence. So what we want to say is a sequence of point converges, it does not yet converge, but it gets closer and closer to an accumulation point. So we have maybe a sequence of points, x1, x2, x3, x4, x5, and so on. In the beginning they can be everywhere, but eventually they zoom down in a small area of the space, and they get closer and closer. This is the intuitive meaning. Now what does it mean in practice? In practice it says you specify a distance epsilon, and then so if I want to prove to you that something is a Cauchy sequence, then you say, well, I give you a distance of epsilon 0.1. Then I say, okay, in my sequence, once we are beyond the index 5 million, I can assure you that no matter which points we're going to look at, they are going to be of distance at most your epsilon. So eventually, maybe I draw another picture here, in a metric space, what you can imagine is eventually there's going to be a little ball of radius epsilon, and if you proceed long enough in your sequence, if the index is high enough, then everything is going to live within this little ball. That's one way of seeing it. If you haven't seen this definition before, I would urge you to play a bit with this definition, and particularly pay attention to the order in which the quantifiers are presented here. This is important. If you change the order of these quantifiers, then you get different meanings. Okay, so such a thing is called a Cauchy sequence. Now I've already said, more or less accidentally, the sequence converges. Now, that is not always true. A sequence sort of gets closer and closer, and we now say a sequence converges if this limit point is also, if there exists such a limit point in our space. So let me write it down first. A sequence xn, like also in the metric space and so on, converges to some point x in the metric space if, now we have a statement that's very similar, for all epsilon larger than 0 there exists an n in n, such that for all n larger than n the distance between xn and this limit point x is smaller than epsilon. And now we not only require that points get closer and closer together, but we require that there's this limiting point x that is also part of our space. And if this is the case, we then use the notation. So there are various notations. You can Often people write xn converges to x with this little arrow. Or people also write the limit of n to infinity of xn is x. And maybe just to give you sort of the few very simplest examples, like assume you have the sequence xn is 1 over n for all n. This is a Cauchy sequence because eventually everything is going to get closer and closer to 0. And it converges to 0, but only if 0 is in the space we're currently considering. So if you consider the sequence, so if I consider the sequence xn such that xn is 1 over n on the space x, which is, say, the space 0, 1, the open interval, then xn is a Cauchy sequence, but it does not converge because the limit point 0 is not part of our space. And so here xn is a Cauchy sequence, but it does not converge. And the reason is that 0, the point where it would converge to, is not in the space we're currently considering. If we now consider the sequence, the same sequence, xn is 1 over n, on the space maybe x tilde, and this is now the space 0, 1 with closed intervals, then it's a Cauchy sequence and it also converges, namely to 0. So here xn is a Cauchy sequence that converges to 0. Okay, that's hopefully enough to get the first intuition or to make you remember what you have probably seen somewhere in your undergraduate math lectures. If you haven't seen that, then maybe try to come up with a couple of examples, and we're also going to do exercises in the assignments, of course. Now let's continue with the topological definitions. So we say a metric space is called complete if every Cauchy sequence converges. If every Cauchy sequence converges. So whenever you have a sequence that is approximating a limiting point, then the limiting point needs to be in the space. And if that is the case, then the space is complete. Now I want to talk to you about what are open and closed sets. So maybe I introduce one notation. By b epsilon of u, this is supposed to be the ball with center u of radius epsilon. So this is the set of all points x in the metric space such that the distance between x and u is smaller than epsilon. And now one needs to be careful. Depending on the context, the definition of such balls is often either it's the open ball or the closed ball, like we have smaller than epsilon or smaller or equal to epsilon. You always need to check which is the current definition of the balls when you read that, and it might even be inconsistent in my lecture because sometimes it doesn't even matter so much which kind of ball we consider, and when it does matter, I typically specify it, but you need to make sure that you always are aware of whether we talk about the ball including the points which have distance epsilon or excluding those points. So this is a ball. And now we can define what does it mean to be open or closed. So definition, a set U in X, so some subset in the metric space, is called closed if all Cauchy sequences converge. All Cauchy sequences converge. The next thing is when is a set open? That's sort of the opposite of being closed. A set U in X is called open. And now if for each point in the set we can fit a little ball around this point which is completely contained in the set. Let me see how I formulated it here. If for all U in U, sorry, I write it in the next line. For all points U in the subset we're currently considering, there exists some epsilon larger than 0 such that the ball of radius epsilon around U is completely contained in X. Again, let me maybe try to come up with an example. So, for example, if we're the set 0, 1 is closed, no matter which Cauchy sequence you can construct in this space, the limiting point is always going to be in this space. On the other hand, if you consider the set 0, 1 with the open interval, this is open. And now the trick is of this definition of being open. So just imagine here is our real line. We have 0 and 1 excluded. Now we can pick any point here, say this is U, and for this particular point we can always find a ball, and a ball in this one-dimensional space is simply an interval. So this is essentially the interval ball. In this case is the interval U minus epsilon, U plus epsilon. And this is contained in the red set. And if this is true for each point on the line, so for each point in the set, we can find such a small tiny blue line that is a bit left and right of the point we're interested in and still sits in the set, then the set is open. Okay. Now observe that there exist sets which are neither closed nor open. Maybe I write this as well. A set U can be neither open nor closed. And the simplest example is the set, the interval 0, 1, which is closed at one end and open at the other end. So here, the set, just maybe consider why is it not open? It's not open because at the point 0, which is part of our set, I could not fit a ball around because it's like I can't push more to the left. So any ball that I would fit around 0 would go from minus epsilon to plus epsilon, but minus epsilon is not in our set. On the other hand, so it's not open. And it's not closed because I can construct a sequence that converges to 1. For example, if I construct the sequence 1 minus 1 over n, this converges to 1, but 1 is not a limiting point, so this is not in our set, so it's not closed. Okay. These are open and closed sets. And now I want to say when is a point an interior point and when is a point a boundary point. So definition. A point U in U is an interior point of U if there exists some epsilon larger than 0 such that the ball of epsilon, of radius epsilon around 0 is in the set U. So an open set consists only of interior points. So every point in an open set is interior by the definition of what is an open set. So this is an interior point, and just looking at the interval, for example, if we have the set U which goes from 0 to 1, then all the points x which are in the open interval 0, 1 are interior points. the only 2 points in this interval which are not interior are the 0 and the 1, because, as I've already said, we cannot fit a little epsilon ball around them. So that's interior point. Now I want to say, what is the topological closure? I write topological in parentheses, topological closure of a set U is defined as follows. So we take all the points, like we start with the set U, we look at all Cauchy sequences, and we add all limiting points to the set U. And the set we then achieve is a closed set, and it is the smallest closed set that contains U. As the set of points that can be approximated by Cauchy sequences in U. And like if you want to see it a bit more formal, we say a point W is in U bar, and we are going to denote the closure with U bar. I haven't said that before. If and only if, for all epsilon larger than 0, there exists some Z in U such that dWZ has distance smaller than epsilon. So we can construct a sequence of points in U that converges to this particular point W. You could also define the set, there are many different ways in which you can define it. You could also define it as the smallest set that contains U and is still closed. Okay, and the notation, I've already used it previously. U bar is the closure of U. So whenever you have a set and we are in a topological context and you see U bar, like a bar above the notation of the letter of the set, this means the closure. Now observe, I said topological closure because there are other contexts in which you also talk about the closure of a vector space. So for example, you could say, in the context of linear algebra, you could say you have a certain set of vectors in our space, and the span of this vector is the linear closure of these vectors. Essentially, you add all linear combinations, which doesn't necessarily mean that the space is closed in a topological sense. So we need to be a bit careful here in which sense we talk about a closure, and this is about the topological closure. And now, once we have the closure, we can also define what is the boundary of a set. So the boundary of a set are now the points which are like the closure point, like you take the closure and you subtract the interior. Oh, sorry, I forgot to say what the interior is. So this is the closure of a set. So I say then the interior, so also topological interior of a set. Set U is defined as the set of interior points of U, and the notation is U circle. I mean, these notations are sort of standard, but maybe some people also use slightly different notations. But I think in topology, this is what you would typically use. And now we can finally say what is the boundary. The topological boundary of a set U is defined as the set U bar, the closure, without, no parentheses, without U circle. Okay, so we take the closure of the points and we take away all the points which are interior points. And let's maybe again do a couple of examples. So if we have, for example, the space X, which is the closed interval. So what else are the, so the or maybe use a slightly different example. We use the half open interval 0, 1. Then the closure of this space is the space 0, 1, where we add this limiting point 1 that we could still achieve. The interior of X is the point 0, 1, so the open interval 0, 1. And now the boundary, now I'm considering the boundary. I'm just struggling with the definition, so because my intuition would have been the boundary of a set U. Now I guess there exist different definitions, so my feeling would be the boundary of X would be X without the interior, and this would now essentially be just the set 0. And I think this is also how we should define it above, otherwise it doesn't really make sense, sorry. So I define the boundary of a set as the set itself without the interior. Because somehow I mean, there are two ways in which you can do it. Whether you first take the completion and then subtract the interior or not. Maybe you again need to look at the context. My feeling is that this is not uniquely defined. Depending on the context, you might look at the boundary. Maybe I write boundary 1. This would be the definition if we take the set itself, and I need to remove X tilde and not U tilde. And we could also have a different definition, boundary 2 of X, which is X bar without the interior, and then this would result in the set 0, 1. My feeling is that there is not a unique definition, and whenever we are going to talk about the boundary, I would prefer the first definition. This one here, this is the one I also have now on the slide. So maybe put this in parentheses. Okay. That's the boundary. And now we have to make not so many more definitions, but I want to say, what does it mean that a set is dense? Yet another definition. A set U is dense in X, in X. So U is a subset of X and it is dense in X. If I can approximate every point in X by a sequence that just lives in U. If we can approximate every point X in X by a sequence in U. And formally, there are many ways in which you can write this down, but here is one. For all epsilon larger than 0, for all x in X, for all x in the space, and for all epsilon in 0, if you look at the intersection between the epsilon ball, around X and U, then this intersection is non-empty. Maybe let's draw a picture. The set, or like an example, the set of rational numbers is dense in the set of real numbers. So this set of rational numbers considered as a subset of the real numbers is dense. And why is it so? I can take whatever real number I want and I can approximate it by a sequence of rational numbers. Okay, and finally, a last definition. So this was dense. Now I want to say, and this is now a definition, so many of these definitions I just made, what does it mean to be dense, open and closed? These are notions that come from general topology and you can apply it to all kinds of settings. Now finally, there's one definition that you can only make if you have at least a metric space, namely what is a bounded space or a bounded set. A set U in the metric space is bounded if there exists, say, a constant d larger than 0 such that for all points u, v in the set, the distance between u and v is at most d. Okay, so bounded is intuitively clear, like no two points in the set can have a distance further than a certain bound, and this is sort of sometimes this bound is called the diameter of the space. The smallest such bound that you can give is the diameter of the space. Okay, that is what I wanted to say about metric spaces, and in the next lecture we are now going to look at normed spaces.